Today we're looking at 3.5, which is complex zeros and the fundamental theorem of algebra. So the fundamental theorem of algebra just says that every polynomial with complex coefficients has at least one complex zero. So in practice, you don't really have to think about this a whole lot because it's a lot like the previous sections where we're just factoring things with just a few additional parts thrown in. So let's look at the first example and we'll just see where it goes, and then maybe this will make a little more sense. So we have this polynomial, p of x equals x cubed minus 3x squared plus x minus 3. And it says find all zeros and factor completely. So I'm going to go about this the same way that I did in the factoring sections before. So the possible zeros are plus or minus 1 and plus or minus 3. First thing I can see, though, if I plug in a 1, I can see that that's not going to be a 0. If I plug in a negative 1, I can similarly see that's not going to be a 0. So I'm just going to jump to 3 or negative 3. Let's try 3 first. So usually I like to look at the ones, plus or minus 1 if I can, and do those without going through the synthetic division because it's faster. Okay, so go through the synthetic division, drop the 1, multiply 0, 0, 1, 3. Okay, so we do get a 0 with that one. That's so 3 is a 0, and let's try that. Well, let's look at what we have. So we have x minus 3, and then this last line 1, 0, 1, 0. The first term is going to be x squared, and there's no x term, there's just plus 1. So far we have x minus 3 times x squared plus 1. Okay, so you can see right now that this x squared plus 1 is not solvable over the real numbers, so we're going to have some imaginary numbers. So what I'll do is just take that one out and just solve that for x. So if I do that, I get x equals the square root of negative 1, and that's the same thing as I. And this is a plus or minus because we have a square root, so plus or minus I. So the zeros, since it's asking the question separately, the zeros are 3, I, and negative I. Those are the zeros, and then factoring is just writing those out as factors. So we have x minus 3 times x minus I times x plus I. So that would be completely factored. Okay, another example. So the difference here is that we're going to have complex numbers in each of these, or most of them, not all of them. Same thing, find zeros and factor completely for x cubed minus 2x plus 4. So factors of 4 that would work would be, plus or minus 1, plus or minus 2, plus or minus 4. Visually, I can see that 1 and negative 1 are not going to work. So it's going to be some combination of the, it's either going to be plus or minus 2 or plus or minus 4. So let's start with negative 2. And just remember to have a placeholder term. So I'll have 1, 0, negative 2, and 4. And go through the synthetic division. Try not to mess that up because then it messes the whole thing up. Okay, so negative 2 is a 0 right there. Okay, I'm going to take these parts out. Usually when I get to the quadratic, I'll do this rather than going through synthetic division again with another number. Okay, so I can see that x squared minus 2x plus 2 is not factorable by just splitting it apart. So let's do the quadratic formula just on that. So I'd have x equals 2 plus or minus the square root of negative 2 squared, so 4, minus 4 times 1 times 2 divided by 2. So we get 1 plus or minus 4 minus 4 times 2 is 4 minus 8, so 4 minus 8. In the radical, we have a negative 4. That's over 2 as well. And so we simplify to get 1 plus or minus. The square root of negative 4 is 2i. 2i divided by 2 is just I. Okay, so the zeros here, I'll write these out right here. The zeros are negative 2, 1 plus I, and 1 minus I. So you still have 3 zeros in a third degree. It's just that we have complex zeros. So on a graph, you won't be able to see the complex zeros because those that is only graphing in the x and y plane. You'd need a different plane to see those. So you won't see zeros of 1 plus I and 1 minus I on the xy graph, but they are zeros in a different way. So our factors, factored polynomial would be x plus 2, x minus 1 minus I, so I'm just plugging those factors in, and x minus 1 plus I. So 3 zeros in a third degree. Okay, so this one says, well, it has this little box, the zeros theorem, right above it. And so that says every polynomial of degree n is greater than or equal to 1 has exactly n zeros, provided that a zero of multiplicity k is counted k times. Okay, so you'll find in this section you have all of these theorems. There's a lot of them. I think there's like 5 in this section. And you'll notice that I'm not really paying a whole lot of attention to those. I'm not going to emphasize those as much because we've already been using a lot of the theorems. It's just that once they introduce complex numbers, that's when you have to have introduction to the theorems. So I'm just going to work through these knowing that I will have complex zeros a lot of the time. Okay, so this one I'm going to do a little differently. So 3x to the 5th plus 24x to the 3rd plus 48x. I'll set it to 0. And I'm going to factor out the greatest common term in this one because everything, the first thing I notice is that everything has an x, and I believe everything's divisible by 3. So let's just do that first. So if I divide a 3x out, this would be 3x times x to the 4th plus 8x to the 2nd plus 16, just 16, equals 0. Okay, so we have 3x times x to the 4th plus 8x squared plus 16. And now we have to factor this 4th degree. And you'll notice I'm not using synthetic division on this one because this one is easier to just factor using other methods. So I will factor this. So 3x, and then this is in the quadratic form. So our x to the 4th, the 4 is double the middle term, which is a 2. So we have a trinomial that's in the quadratic form. So I can split this apart by making those both x squared in the parentheses. And two numbers that add to 8 but multiply to 16, well, those are going to be plus 4 and plus 4. Okay, so from this we have x squared plus 4. And I'm not going to use the quadratic or anything. I'm just going to take one of these out and solve them so that we can see what the zeros are. So I subtract 4, solve for x. So x equals plus or minus the square root of negative 4 or 2i. Scoop that over a little bit. Okay, so I just solved for 2 of the zeros right there, but we have 2 identical terms. So 3x times x squared plus 4 times x squared plus 4. So what we can do is just write those twice. So all the zeros would be, well, the first 0 is just going to be coming from this 3x. So x equals 0. So that's one of them. And then we have plus or minus 2i and plus or minus 2i. So those are duplicates. So this is a fifth degree, and if you add up all those zeros, we have five zeros. I was going to call them roots, sorry. And so we have x times x minus 2i times x plus 2i. And if I really want to write all these out, I can, but you could also just put squares on these. Okay, so 5 zeros. 4 of those are complex zeros, so on an xy graph, you'd only see the one at 0. And that's it. So that problem I did a little differently. So the two things I did differently were I did not use synthetic division, and I didn't use the quadratic formula because I didn't have to. So I only use those things when I have to because those are more work than what I did here. So our next example is a little bit different. Find a polynomial p of x of degree 4 with zeros I, negative I, 2, negative 2, and with p of 3 equal to 25. So this type of problem you do the same way each time. So first thing we do is write out p of x equals a, and the a we need later for solving for the condition p of 3 equals 25. And then we have x minus I times x plus I times x minus 2 times x plus 2. And we do need to multiply these out. So I'll have a, and if we multiply each of these, they're both differences of squares, so we can use that fact to make it faster. A minus I, or x minus I times x plus I is going to be x squared minus I squared. Since I squared is negative 1, you'll get x squared plus 1. So that's a shortcut. X minus 2 times x plus 2 is going to be x squared minus 4. Now what we want to do is multiply these out. So we'll have a times x to the fourth minus 4x plus 1x. So x to the fourth minus 3x squared minus 4. Okay, now that we have that, we have this p of 3 equals 25 to deal with. So we're going to take 3 and plug it in. So we'll have p of 3 equals a times 3 to the fourth minus 3 times 3 to the second minus 4, and that's going to equal 25. Okay, so I'll simplify that. That's 81 minus 3 times 3 to the second minus 4, that will be 50. So we'll have 50a equals 25, and a is then 1/2. Okay, so we haven't found the polynomial yet, but what we're going to do is go back up to this line. So we have a times x to the fourth minus 3x squared minus 4. And that's where we're really going to plug that 1/2 in. So I would have p of x equals 1/2, and I'll distribute as I do this. So 1/2 x to the fourth minus 3/2 x to the second minus 2. Okay, so we have the conjugate zeros theorem. This is a lot easier than what the theorem sounds like, so I'm going to read it and then I'll translate it. So if the polynomial p has real coefficients, and if the complex number z is a 0 of p, then its complex conjugate z bar is also a 0 of p. Okay, so that's like a lot of the theorems. It's written in a very technical way, and if you're not familiar with that type of writing, it doesn't make any sense. So all that means is that that complex zeros come in conjugate pairs. So if you have, in this case, so this example is find a polynomial p of x of degree 3 that has integer coefficients and zeros 1/2 and 3 minus I. So you'll notice this says a polynomial of degree 3, yet it only gives you 2 zeros. So one of the zeros is a complex number. So you'll also have the 0, which is 3 plus I with that. And before I solve and go through this problem, this is kind of a long problem. Just remember that conjugate or that complex numbers come in conjugate pairs because they're ultimately, they come from negative numbers under a radical. So if we take this expression x squared plus 1 equals 0, solve it for x, we're going to get, subtract 1, take the square root. And when we take the square root, you have to go plus or minus. So every time you take the square root of something, you have to have the plus or minus out front, which means that there are two zeros and they're conjugates. So they have opposite sign. So with this problem, 1/2, 3 minus I, and 3 plus I are the zeros. This does not give you any specific condition like in the last problem, like the P of 3 equals 25. So what we have to do is go ahead and solve it in the same way, but we leave A alone. So we have P of x equals A times x minus 1/2 times x minus 3 plus I and x minus 3 minus I. Okay, so that is a polynomial of degree 3, but we do have to multiply this out, so it's obvious that it's of degree 3, because it's possible for some problems that the x might cancel out, like your square, or one of the x's could cancel. So we do have to go through the multiplication and all that. So I'm going to try to use some of the difference of squares ideas here. Okay, so let's focus on the hard part. These x minus 3 plus I, x minus 3 minus I. If I put parentheses around the x minus 3, you'll actually see that those two are conjugate pairs. So we can use the difference of squares with these. So we have the plus I minus I. So let me rewrite this part. So a times x minus 1/2. And rather than distributing all of these terms and taking forever to do that, I'm going to use this idea. X minus 3, that's going to be squared. Okay, minus I squared. So what I did just now is use the idea of a difference of squares to multiply that together. And now it's a little bit easier in the next step. So a times x minus 1/2, and then x minus 3 times x minus 3 is going to be x squared minus 6x plus 9. You can check that. And then we have minus I squared. So I squared is -1, so this is plus 1. Next line, a times x minus 1/2 times x squared minus 6x, and I'll add the 9 and the 1, so this will be plus 10. So I eliminated a lot of work by using that difference of squares idea. Okay, unfortunately now I can't do that, so I'm going to leave the a and I have to multiply all these terms out. So I'll have x cubed minus 6x squared plus 10x minus 1/2 x squared plus 3x minus 5. Okay, so then we have to, condense that. So a times x cubed, negative 6x and negative 1/2 x squared. So our squared terms, we have to make a common denominator. So that would be negative 13x squared over 2 plus 13x minus 5. Okay, so that's our final answer, and we say a can be anything. Okay, we have yet another theorem here, and again, you don't really need to know this to go through these problems, but it does help explain what you get at the end. So the linear and quadratic factors theorem says every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. So in this problem, that's what we're going to do. We're going to factor it. X to the fourth plus 2x squared minus 8. It is a trinomial in the form of a quadratic, so we can factor that like a quadratic. So we get x squared plus 4 times x squared minus 2. Okay, so for this one, the x squared plus 4, I'll go through and solve that even though I don't really need to, I don't think. So x squared plus 4 equals 0, and x squared minus 2 equals 0. All right, x squared plus 4, subtract the 4, take the square root. So x will be plus or minus 2i. So we have 2 zeros there. On the right, x squared minus 2, we add 2 and take the square root. So x will be plus or minus the square root of 2. Okay, so we have found the zeros, and we just write those as factors. So x minus 2i times x plus 2i times x minus root 2 times x plus root 2. Okay, so we factored that into a product of irreducible factors with real coefficients. So that is the answer.